If anyone has any suggestions for me, I would gladly take them, but you're here, so.
You're great. Thank you.
Reminder of the big four. First one, come to every class. Do every pre-work, aim for 75% or higher on my math labs, spend 15 hours a week on the course, working through it, and then work each of those MyLab open math quizzes. Okay? There's a tendency to kind of just try to find a shortcut way through them. Folks, come an exam, there won't be a shortcut way through the problems, so this is meant to get you ready. These are the types of problems that I'm saying you absolutely need to know how to do these problems. Okay? All right. See here, due tonight you've got your quiz 5, first attempt of the MyOpenMath. And after today we'll go through the 16.1, 16.2. Go ahead and get started on that. MyLab Math, that's due, I should add there that that's due Sunday evening. We're going to stay skipping 15.7, 15.8. We'll pick those up when I can. Okay. Yeah, 15.7 as well. We're just the max mins and the Lagrange multipliers. We'll pick those up when we get a chance. There we go. I think that's everything. Okay. Yeah, Nate.
Will you move the homework for 15.7?
I already. Yeah, I did. I moved it to the last day of the semester. Please, folks, I put it the last day of the semester to put it somewhere. Okay. It will eventually get moved forward, right? Okay, but let's. I want to get into this multiple integration. That's what we had the pre-work going for, so it made sense. These two sections really go hand in hand. So let's go ahead and get started on this. Everyone should have a copy. If you don't, I've got more up here of the 16.1, 16.2. Okay. There are two things we need to learn. One is how to do multiple integration. And in some ways, because we saw in our pre-work that we can reduce these to iterated integrals, in some ways it's not too hard to do multiple integration. Okay? But it is just like before, it is absolutely essential we have the concept of what we're doing down with these problems, and that's what I want to spend a bulk of the time today working on, is the conceptual understanding, and then we're going to have the rest of the course to get better at multiple integration. We'll basically be doing multiple integration from now through the end of the course. Okay? So in this case we've got the region R, and it's described to be a region in first and fourth quadrant, bounded by a semicircle of radius 4, centered at 0, 0. Okay? So I do expect you to know how to come up with equations for things like circles and semicircles, etc. I think the easiest thing to do here would be to give yourselves a quick sketch. So if we were to give ourselves a quick sketch here, there's the, up to my ability to draw a semicircle. There should be about there, our region. Oops, let's shade it. So we're in quadrants 1 and 4, and we've got a semicircle of radius 4. Okay. So let's go ahead. We're going to set this up to do multiple integration on this. You can see that I'm asking you to evaluate what type of integral down here, folks? What type of integral is that?
Double.
We're calling that a double integral. Okay. And I know that quickly we move away from these. As soon as we can, we start writing them as iterated integrals. But that's only because of whose theorem? Fubini's theorem. We saw that in the pre-work, right? So that's what allows us to rewrite in certain cases, and most of the cases we'll deal with it here. In certain cases, you can rewrite double integrals as iterated integrals. If not, you'd have to come up with some other clever way of trying to evaluate that particular integral. Okay? So this is what we want to evaluate. We want to integrate over this region here. Okay? So I think it's really important as you're working through these to, let's go ahead and label the positive x-axis here, positive y-axis here. It's really important to keep in mind that we often don't draw the whole picture. The function that we're integrating over is kind of the least important part of our problem in a lot of ways. Okay? So you can imagine, some function here. And in this case, this is not what our function looks like, but we've got some f of x, y that we want to integrate, but we're not integrating over the entire xy plane. We're integrating over this region R here. Let's go ahead and label that region R. We've got this region R here, and our region R would look something like this. Now, what's an interpretation of what we're doing here? When we're evaluating this integral, what's an interpretation of this? So when we're done computing this, we're going to get a number like 15. What's an interpretation of that number 15? We can interpret that as the volume between this function here and the region in the xy plane. So we can interpret that as a volume. So this would look, look something like this. It's kind of morphed because of the, not a great drawing, but that'll work. Okay. And so an interpretation of that is we're computing that volume there. Okay. But you can see that I could do several problems where I just keep changing the function f of xy above, and we will still be integrating over the same region in the xy plane. Okay? This was kind of like the limits of integration were sort of the least important thing of your work in Calc 1 and in some degree a little bit in Calc 2. The limits of integration were they were obvious. Okay? And doing the integration was the hard step because you had to learn how to take these antiderivatives to be able to use the fundamental theorem of calculus, right? I think that it's kind of back, the difficulties kind of flip-flopped here. Okay? You're not going to get some messy integrals, although we could certainly give you messy integrals that require all sorts of substitution techniques. And we will do some, don't worry. Don't worry, you're not going to get cheated out of them. But the harder part will be coming up with your limits of integration. Okay? And I'll give you a hint. If you're not getting the right answer and you haven't sketched your region, I know where you could get started. Right? If you don't get the right answer and you haven't sketched your region, I know exactly where you can get started. And I'm doing this right off the bat, folks, because when you go to work your MyMathLab problems, we're going to start off with a rectangular region. And those problems are going to be deceptively easy for doing the iterated integrals with. Okay? So I'm trying to focus your attention on these non-rectangular regions because this is the hard part for this section. All right. So we've got two different ways of talking about these regions. I call them type 1 and type 2. Folks, that's my own notation. Or I shouldn't say, I think I took it from a different textbook. But our textbook doesn't use that notation. And frankly, it doesn't really matter which one you consider type 1, which one you consider type 2, as long as you understand that there's a difference in the order in which you do the integration. Okay? So let's consider this first as a type 1 region. So we're going to be looking at the collection of ordered pairs, x comma y. And what do we need here? Well, in this case, we would look at our x coordinates, and they are going between 0 and 2. Oops, 0 and what? Not 2. 0 and what? 0 and 4. And we'll go back to draw. Let's just recopy that. Let's recopy this image. Let's see if I can make a copy. No, we'll just recopy it because you don't have to do it too. Let's just recopy that semicircle here. Okay. And what I'm talking about when I'm thinking about this as being a type 1 region is I'm talking about first selecting an x coordinate and then allowing y to vary for that x coordinate. Then I move over and I select another x coordinate and I allow y to vary within there. I think it's really handy, and you guys maybe remember this from Calc 2 when you did the, remember when you did the volumes of revolution, how important it was when you were deciding which order in which to integrate, to draw a region, and 2, I think you should draw little slices through that to help you imagine what we're doing. So as far as x is concerned, my x coordinates are starting where and stopping where? My x coordinates are starting at 0 and stopping at 4. Now, don't write this down. The classic mistake that a student will make at this point is they'll say, and my y coordinates go between here and here. Don't write that down. It's wrong. The classic mistake that students will make at this point is say, my y coordinates are going to go from -4 to 4. What region did I just describe there? That's a rectangle. Okay? That's a rectangle there. That's not this semicircular region. So always, folks, once you write this out, do a double check. Make sure that it makes sense, and don't fall in the trap of, it is true that my smallest y-coordinate down here is what? -4. My largest y-coordinate is 4. That part's true, but what's actually determining where the y-coordinates start for one of these slices? Let me do this in a different color here. What's actually determining where one of these y-coordinates begins and ends when I take one of these x slices? It's the boundary, which has to do with that semicircle. And you need to be analyzing these pictures this way. Okay. All right. So it looks to me like my y-coordinates start when we hit this lower semicircle here. Okay. So remember that the entire circle would be the circle x squared plus y squared equals 16. And do we need to review upper or lower left and right semicircles? Should we review that? Sure. Okay, so that's up to you. So if I take the circle x squared plus y squared equals 16, if I solve this for y, I get y is equal to plus or minus the square root of 16 minus x squared. So what we have here, in fact, I'll do the plus in red and the minus in blue. What we have here then is this description for the upper semicircle and this description here for the lower semicircle. The plus, the upper, the positive root gives me the upper semicircle, the negative root gives me the lower semicircle. If I were to take this same expression, x squared plus y squared equals 16, and solve it explicitly for x, I get x is equal to plus or minus the square root of 16 minus y squared. Okay? And let's do this. Let's play the same game here. We'll do purple and green. And so what have we found here? X being a function of y, we pick a y coordinate and it outputs an x coordinate. This will only output, the purple will only output positive y coordinates, or excuse me, say that again. The purple will only output positive x coordinates, so that's this right semicircle, and the green will only output negative x coordinates, so that's that left semicircle there. We okay with that, folks? All right, make sure you have that down. So in this case, what I want, when I'm integrating with respect to x here, folks, this is for the type 1. So I drew my slices running, the slices run along the x-axis, right? So I pick an x coordinate and then I figure out what's my minimum y value of that slice, what's my maximum y value of the slice. That has to do with hitting the semicircle. And so that's going to be from minus the square root of 16 minus y squared, x squared, less than or equal to y, less than or equal to the square root of 16 minus x squared, the positive one. Okay? And there I took the upper and lower semicircles. Questions on that, folks? Sorry I didn't give you quite enough room.
And it's restricted to the right semicircle
Well,
because of the x.
Go ahead.
That we're given? Like because of the x being between 0 and 4, it restricts it on the right side, even though on y is both the top and the bottom.
Correct, because so we don't get this doesn't give us the entire, like if we just said this, or if we said x is going from -4 to 4, then that would give us the entire. We wouldn't have to say that because it would be applied, but that would give us the entire circle. So the combination of those two restrictions is what gives us that right semicircle. Sorry, and let me clarify, folks. I want to make sure I said the right semicircle. I really ought to say the right semicircular region. Okay, it's very important. These are not, y is not equal to these values. Y is between those values. Okay, these are regions that we're describing, not boundaries of regions. Although we could stop and we could talk about boundaries of regions, we're talking about the entire region here. Okay, so go ahead and give me the other way of describing this region. give it a shot, and then I'd like you to check with folks at your table.
I don't know, I think it's zero because we're just if you do that. So if you have negative square root here, I think you're right. Because if you're starting at zero and then first I thought that they were just interchanging between x and
Ah, so you gotta be really careful there. That's not the case, and that's a common misconception. Great, I love that you've drawn a region there, and now you're drawing your slices. That's the way to do it. Folks, how many of you find this a little more difficult than maybe you thought it would be? Potentially, that means you've got some practice to do, and now you kind of have a gauge for how hard this is. So I'm working through these problems. I'm just doing them. Okay, I'm going to try to talk you through them, but you may not know how challenging they are until you try to do one from scratch. Okay? So, if you found yourself having trouble, did you redraw the region and then draw some slices? If you didn't do that, that's my first piece of advice. Okay? In this case, we're going to consider this as a type 2 region, and so we're going to look at slices parallel to the x-axis, meaning we're going to be moving those slices up the y-axis there, right? And so what are my y values doing? They are ranging between what and what as I do that? My y values are ranging between -4 and 4. -4 is less than or equal to y, which is less than or equal to 4. Okay. Any questions on that? Now, what are my x-coordinates doing? The mistake would be to say my x-coordinates are going between 0 and 4. If I did that, what would I just describe? A rectangle, which is not the case here. Will it be the case for some of your 16.1 problems? Sure. But this is not a rectangular region. The best piece of advice I have for that is to go ahead and sketch out one of your slices and ask the question, where did my x values start and where did they stop? And if you can't see a pattern there, do one more. Where did they start and where did they stop? So it looks like always my x values are going to start where? At 0. So that would give us 0 less than or equal to x, which is less than or equal to, and then where do they stop? When we hit the semicircle. But I have to describe the semicircle in terms of the fixed y-coordinate that I've got, and so I've got to solve the semicircle for x in this case. And if we solve the semicircle for x, we've got the square root of 16 minus y squared. Okay. An important, David, you might be pointing out, an important thing to realize, folks, is that in some cases, it'll be very easy to interchange between regions. But in general, I don't look for some pattern to quickly switch from this region to this region. I start over from scratch. And I highly recommend you do that each time, rather than trying to find some sort of pattern in there. Are there patterns to be had? Sure. It's not worth looking for them. Okay? Instead, just redraw the region from scratch. All right. So what I'd like to do here is let's go ahead and integrate this first as a type 1 region, and then second as a type 2. I said to do half the class. Let's have you all give it a shot. Just try integrating first the type 1 region. Set up the double integral and give it a shot. check the answer. 64. Has to do with that. It has to do with the soft description. Look at the notes going by. I like. Okay, let's see what there. Great. I like that you're labeling the limits of integration. It's a good idea. So good. Great. I disagree. In fact, you've got the limits of integration as you read the type 1 region that we gave. Correct. Very good. Look here. Great. I like that you've got that. You're setting those up. Good. So then, what will it be for the type 1 region then? Very good. No, you cannot. So this is where, yeah, it's a great question. You want to be a little bit careful. In Calc 1, we emphasize looking for symmetries, and same thing sometimes in Calc 2, we're looking for symmetries. But this function is what's, the function, your region may have symmetries, and that's important, but the function also needs to have symmetries. The function that lives above this is not necessarily, and in fact is not symmetric. Maybe there is a symmetry here, I'm not sure, but it has to do with the function that lives above it. Yep. Folks, let me get your attention, please, as you're setting these up. I do recommend, I'm not going to require it, I do strongly recommend you label the variables for the limits of integration. It keeps you in the right mindset. Folks, tomorrow's pre-work involves doing these with polar coordinates. Once we learn triple integrals, which was next class pre-work as well, we will then eventually switch over to different coordinate systems, including cylindrical and spherical coordinate systems. You're going to have a lot of different variables, and I recommend getting in the habit of labeling your limits of integration there. Not a requirement, but it's at least, you know, and sometimes what I'll do is I'll label them for the first integral, and then I'll stop writing them after that. But it at least grounds you. If you find yourself making mistakes, I recommend that. The other thing is this part is not required. But I'm going to, for this first problem, I'm going to put parentheses around that iterated integral. It helps you think about it correctly. When I'm done evaluating the inside parentheses there, I'm going to have a function that only depends upon what variable? Yeah, this whole thing will depend only on x when I'm done. It'll be a function of x. And so then it helps you see that iterated integral sitting in there. Not a requirement to put those parentheses in, but a recommendation. Okay. Integrating that innermost integral, we get the integral from 0 to 4, and then when I integrate that innermost integral, I will get just x y squared evaluated between y equals minus the square root of 16 minus x squared up to y equals positive square root of 16 minus x squared, and we'll integrate that result with respect to x. In this case, something nice happens. We've got x times, and then for the y squared, let me do it this way. There's lots of ways to sort of shortcut your notes as you're working through this. We'll do x times that first expression, which is just 16 minus x squared, minus x times this second expression squared, but even though there's a minus root there, when I square it, I still end up with 16 minus x squared dx. Technically, I need another parentheses in there. I'm not going to write it. I guess I should. There's another parentheses in there. But notice that that's an expression minus itself, and so we're integrating from 0 to 4 the function 0. And what's the area underneath the curve of the function 0 between 0 and 4? Oh, I'm getting a lot of looks here. First of all, any questions going from here to here? So any questions about why the integrand is 0? All right. Folks, you can do this however you want, but the easiest way is to say if this is x, and this is some function a of x, and to say that this is the function 0, then we're saying what's the area underneath this curve between x equals 0 and 4. Well, what is that area, folks? What's the area between the purple curve and the x-axis between 0 and 4? 0. We okay with that? You know, or you could say when I integrate 0, I get a constant, but then when I evaluate the constant at 4 and subtract from it evaluating the constant at 0, I also get 0. Great. That's nice. For practice, I want you to go ahead and evaluate the other way, but let's just set it up. So if we set this up as a type 2 integral, and again, folks, I'm only using the types as we're in class. It's not a requirement, and I won't hold you to know this is type 1, this one's type 1, this one's type 2. Just know that there's a distinction. Okay? So if we evaluate this as a type 2 integral, it'll be the integral from y equals 0 to y equals negative 4 to y equals 4 of the integral from x equals 0 to x equals the square root of 16 minus x squared of 2xy dx dy.
Should it be 16 minus y squared?
16 minus y squared. Thank you so much. Does everyone see where I'm reading this from? I'm reading it from my description of the region that I gave right there, when I described it as a type 2 region. Okay? If I didn't write this out, and I recommend writing this out for a while until you're kind of bored writing out the region, if I didn't write it out, where I'd be getting it from is from the region that I drew right here. My y coordinates were going from minus 4 to 4. Then for any fixed y value, my x coordinates were going between 0 and when we hit the right side of that semicircle. So this would give us the integral from minus 4 to 4 of of x squared y, evaluated from x equals 0 to x is equal to the square root of 16 minus y squared. You know what? We're almost done. Let's just finish it. dy. And so this would be the integral from minus 4 to 4 of 16 minus y squared times y minus 0 dy. Where the integral from minus 4 to 4 of, let's see here, we get 16 y minus y cubed dy. Now, at this point, if you recognize certain symmetries, you can go ahead and use some. Okay? In this case, I'm integrating this truly is an odd function with equal opposite limits of integration, and so you could make a jump as to what the answer is. Okay? But I'll just go ahead and finish this out since it's been a while since I've done some integrating anyway. This would give us 8y squared minus 1/4 y to the 4th, evaluated between minus 4 and 4. And let's see, that's 16 times 8. 16 times 8, I think it's 128. So we get 128 minus, and then 256 is 64. What am I doing wrong here? Oops. Yeah, good. Minus parentheses 128 minus 64, which leaves us also with 0. Questions on that, folks? A comment that I want to make is that oftentimes you are looking for symmetries to try to make integration easier. And while you can still use symmetries, there's more that you have to be keeping track of here. You have to notice the symmetries in the region that you're integrating over. That's true. But then you also have to notice whether there are symmetries in the function that we're dealing with. Okay? And I think that it would be a little bit hard to try to make shortcut rules based on some of these symmetries that we saw here. Okay? Yeah, Andrew.
So you said we don't need no type 1 and type 2 necessarily for the test.
I will not say, do this as a type 1 integral, tell me the appropriate type 2 region.
Yeah, you just
Yeah.
wanted us to do the double integral.
Well, yes, but you're going to have to be able to, you'll have to decide, oops, you'll get started down the problem, you'll say, oh, I thought I would integrate this with respect to x first. It makes more sense to change the region.
Sure.
Yeah.
Okay.
Yep. Yeah, great question.
So since our integral came out to be 0 in both cases, that does mean that the function is symmetric, right?
I'm not sure. I think that you can have I'm not sure about the symmetries of this. I haven't sat down and kind of come up with rules. Is this an even or an odd function for when we're dealing with multivariate functions? I haven't really sat down. I know some shortcuts. I can spot even and odd functions like the sine of x. I know to be odd, cosine of x, I know to be even. In this case, it looks like we do have an odd function here that we're integrating over, and so I think you might be able to make a shortcut with that, yeah. But I'm going to discourage you from doing that because a lot of times people just look for symmetries in their region or just look for symmetries in their function, and you need to be looking at both. Yeah. What else was I going to say here? I guess that's good enough. All right. Okay, so here's a reminder of our process. And I think, like, conceptually, in a few ways, I mean, like, if you felt comfortable with what we did in Calc 1, this isn't really a huge leap forward as far as the idea goes, although it will be a leap forward in terms of notation. Okay? So the idea is we've got this surface here, and our goal is to find the net volume between this surface and the xy plane. So our goal or our strategy is to subdivide our plane or our region within the plane into small rectangles. Then for each one of those rectangles in the plane down here, let's pick one back a little bit. In the plane down here, we've got this rectangle in the plane, and we're going to plug it into our, we're going to plug some representative point from within that rectangle into our function that will output the height of that point, which we'll use as a stand-in for the height of that entire column, and then we know how to compute the volume of a column. What is it? It's the area of the base times the height, and we get the height from the function. Now, that's not accurate. That isn't actually the volume here, but in limit, as what we're going to say is refine our partition, as we further subdivide the plane into more and more rectangles, then what we notice is that as we compute the sums, as we sum up the columns, the volumes of each of those columns, we get a value that appears to be approaching some limit, and that limit is what we call the volume of this surface. Yeah.
What are those subscripts say?
Those are x star, y star.
Okay.
Yeah. And so that the stars refer to just some representative point within the region. So what I'm saying here is if we looked at this, we'd have this region here, and we further subdivided it into little pieces. And then say for this piece right here, I'm going to take any point from within that rectangle. and use that as a representative point. So usually when we're referring to the x and y coordinates of that representative point, we often put a star on it, and we may even put subscripts on it as well, which we'll do in a moment. Yeah. Great question. Oh, it was too far zoomed in. Everything we need is right here. Sorry, folks, I was too far zoomed in. So again, here we've got our region chopped up, and we take, if we want to compute our approximation, or if we want to come up with the volume of this column here, which we're going to use as a stand-in for approximately the area underneath that, or excuse me, approximately the volume underneath the surface and that rectangle. We take some xk star, yk star, assuming that we're talking about here, this is the kth rectangle in our domain. The difference is, in Calc 1, we were just dividing a line into sub-intervals. Here we're dividing a rectangle into sub-rectangles. Okay? And actually this gives us a way of extending it to higher dimensions. Okay? And you'll see that in your pre-work for next time. So then when I want to talk about, so here's how I chop up my region into its k rectangles. I take some representative point from within that, and then I can compute the volume of the kth column by simply taking the area of that kth rectangle there, that's the a sub k. That's the area of that kth rectangle, and I multiply it by the height of the column using that representative point. Any questions about that basic idea? Yeah, Anna?
That representative point can be any point?
It can be. And so what we need to show, I mean, we will not do this in this course. What we need to show is that it doesn't matter which representative point you pick from within there. And in limit, it ends up not mattering because what we do is we add more and more rectangles in our domain, and we make we'll say in just a moment, that the diagonal of those rectangles has to go to 0. Okay. And so in limit, it's kind of the same thing when we chopped up. It's easier to talk about actually in Calc 1 when we chopped this up, and we chopped it up into subintervals, and then from each subinterval we took some point, and they didn't, if you always took the right side of the subinterval, then you were doing the right endpoint method.
Yeah.
And if you always took the left side, then you were doing the left endpoint method. But there's actually nothing that said you had to pick the left or the right or even the middle point. You could pick any point from within the interval. Yeah. And so here we get the idea of refinement, folks. Hopefully we see that as we take more and more rectangles in our, careful, when I'm using rectangles, I'm referring to what, folks? The domain, right? When we're taking more and more rectangles in the domain, that's giving us more and more columns to use to approximate the volume. And each time this is called a refinement of our partition, and we get a better approximation for the volume in limit. Okay? All right, so we're going to say that what is this double integral? Okay? And the same thing happened in Calc 1, folks. If you go back and look at your Calc 1 notes, where we started off doing a finite sum. So here's this finite sum right here. Does everyone see the finite sum before I take the limit? Okay. Before I take the limit, I'm adding up k columns here. Okay. Adding up the, sorry, let me say that one more time. I'm not adding up k columns. I'm adding up the volumes of k columns. Okay. So notice that this is the area of the base of the kth column. This is our height. Pick a different color. It's a little rough. This is our height of the kth column. And so then what's this right here? When I multiply the base of the kth column by the height of the kth column, the area of the base by the height, what does that give me? That gives me the volume. That product there gives me the volume of the kth column. when I add all of those up, that gives me my approximation of the volume. So I wrote add up the n columns. Okay. Then I'm going to look at the limit as delta approaches 0. Okay. This whole expression here, yes, at first glance it looks messy. I'll give it to you. And so rather than writing this whole messy expression every time, what we'd rather do is give ourselves a shortcut notation, which is this notation right here. Okay, and the same thing was done in Calc 1, where we took the limit of the Riemann sums, we called that the definite integral. Okay? So first of all, this is a nicer way of writing this messy expression. But you're getting far enough along in your math career, you really need to be able to parse out these long math expressions and see, aha, that's an area, aha, that's a height, their product is a volume, I'm going to add them up, and then we need to talk about this limit part here. Okay? Here, delta is the length of the largest diagonal across all the diagonals of all the rectangles in the domain. Now, if you're using a systematic way of chopping things up, you don't have to be careful. But if you weren't systematic in your way of subdividing the domain into these rectangular regions, you're going to have rectangles with different length diagonals. And what we're going to do is we're going to look at the limit as the width of the largest diagonal goes to 0. All right. So again, let's say it like this. Let's let f be continuous over a, now we're doing this right now just for rectangular regions. A rectangular region in the xy plane. Folks, how do you describe a rectangular region in the xy plane? Well, first of all, it's a region, right? So that makes it a collection of what? Region is a collection of points. Yep. It's a collection of xy points such that, and then if it's rectangular, it's not going to be like the very first example that we looked at. This example right here was not a rectangular region, right? And if our region is rectangular, what it means is it's got fixed bounds. We say A is less than or equal to X, which is less than or equal to B, and C is less than or equal to Y, which is less than or equal to D, for some collection of values. Folks, one thing I would strongly encourage you to start thinking about is whenever you describe a region this way, to see it as a rectangle. Now, I think that with x's and y's, you feel pretty comfortable with that. So again, if we were to actually depict that region here, here's A, here's B, here's C, here's D, and we can sort of see how that, without too much difficulty, how that gives us a rectangular region, right? I want to point this out because when we start changing coordinates, our region may not look like a physical rectangle in the way you and I describe a rectangle, two parallel lines, right? But when we describe the region, a lot of times when we do our change of coordinates, the new region will have bounds where I've got a number less than one of the variables less than a number, and a number less than the other variable less than a number. When you see something like this, you should think about it as a rectangle, even if the picture isn't rectangular. If you can describe the region as two variables, each of them bound between two numbers, then you should think of it as a rectangular region. And that's going to explain why we do our change of coordinates in later sections. Okay. All right. A partition is formed by dividing R into subrectangles. To do so, we partition the interval AB into P subregions, and we partition the region CD into Q subregions. Okay. That gives us a total of P times Q, or N subrectangles. Okay? So if you look down here, folks, I've partitioned this into 1, 2, 3, 4, 5, 6. On the interval from A to B, I've broken it up into 6 subregions. And if you look at, on the interval from C to D, I've partitioned it into 1, 2, 3, 4, 5. 5 subregions, giving me a total of how many rectangles? 30 rectangles. You okay with that? Okay. Notice in this case, unlike the previous example, I don't have all of the rectangles looking uniform. Okay. All right. Notice that in this general formulation, there's nothing to say that the subrectangles are the same size. That's what we just saw. All right. One issue that I am not going to go through, which you will eventually do if you go back to do more math classes. You take what's called advanced calculus, where you go back and you prove all of this, is the issue of renumbering these. Okay, so this right here we would refer to as the ijth rectangle, and we could refer to this coordinate, this point right here, as the coordinates xi star, comma, yj star. Please don't let your eyes glaze over, folks. All I'm saying here is that since I've subdivided this, I need to refer to the x coordinates in this list. So I've got all these x coordinates here, this one, this one, this one, and this one. All of these x coordinates here, and I number them. This is x of 0, this is x of 1, this is x of 2, 3, 4, 5, and 6, and I'll be referring to them at different instances. Okay? So this is the ijth rectangle, and this is the point xi, yj. Okay? What we need to do, though, is we need to go through and renumber everything, and that's something I want to avoid doing. We go through and renumber everything, so rather than calling this the 1, 1 rectangle, this would be the 1, 2 rectangle, the 2, 1 rectangle. Let me say it like this. I'll just call it the 1, 1 rectangle. This is the 1, 2 rectangle. Do commas. 1, 3 rectangle. This would be the 2, 1 rectangle, the 2, 2 rectangle, etc. Right? Rather than numbering them that way, what I want to be able to do is refer to them by just the number k. So we go through and renumber. This is rectangle 1, this is rectangle 2, dot, 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 and we just call this the kth rectangle. Now that can be done, but actually it's a mess to actually go through and renumber everything that way. And so then this ordered pair we'll refer to as the ordered pair x of k, y sub k. Oops, and I should put stars on there. What does the star mean? It means it's just any old representative point from within that kth rectangle. Questions on that?
Why is it x of I star, like, in the
So-
first picture, why is it?
So,
Is it because it's between j?
well, look at how the subscripts are labeled here. Because this rectangle right here is in the second. It's in the second. I'm sorry. It's in the. Folks, I got an error here. I'm sorry. Let me fix these. This should be 2, 1, 2, 3. This would be the. Oh, I cannot do this to save my life. Sorry, folks. 2, 1. 3, 1, thank you, appreciate it. And this is 2, 1, 2, 2, and then this would be 2, 3. Nope, I did it wrong again. Folks, I'm having a hard time doing this. I'm sorry about this. 1, 1, 2, 1, 3, 1, 2.
2, 2. Or 2. 2, 2.
1, 2, 2, 2, 3, 2. I'm so sorry, folks. I'm sorry about that numbering issue. This is actually, and this is why it is kind of a pain to go through and do this renumbering. Okay, so this would be, so notice that the x column that we're in is different than the y row that we're in. And that's why I use different subscripts. So maybe this is the second x column, third y row, or something like that. Or the third x column, second y row. That would be referring to that there.
Does I have anything to do with the one on the bottom?
Yes.
Well, why is it x sub I instead of x sub I?
So if this is just a numbering issue. If I call this the one I want to talk about, then what would I call the one before it? That number minus 1. So if I want to talk about this x coordinate right here, say it's x of 20. What's the one that comes before it?
X nine.
How'd you get there? You subtracted whatever this was by 1 to talk about this one.
So is it based on the endpoint that's like through the one? Because technically in the rectangle we can touch it both.
Yeah, so that's another numbering issue. You have to decide how are you going to count. Are you going to call this the, if you call this x, you're going to call this x of 0, or are you going to call it x of 1? And that's an issue that you have to decide on. And that's why it's another reason why this whole numbering issue is so frustrating. Yeah, go ahead.
So for the point, can you write x sub I minus 1 star, comma, y?
If that's how you want to, I don't know why I'm getting
I'll
this.
fight the board.
I don't know why this is going on. All right. Yes, there's other ways you could number these, and there's other ways you could label them, right? The question is do I call this the first step or the 0th step? Am I going to refer to it as the first rectangle or the 0th rectangle? And that's something I'm not spelling out, which is partially why we're having questions on it. But I promise you, if I were to spell it out, it would take pages to spell out carefully to then go through and renumber everything. Yeah. So that at the end of the day, we want to forget about this issue that you're struggling with right now and simply say, let's call this the first rectangle, this the kth rectangle, and then we can just refer to the points as xk star, yk star, and we don't have to worry about that whole issue. Wait, which one are we talking about here? Yeah, yeah. Now, if that's the case, though, we could say that this would be, let's just leave it at that. All right. So what's the area of the kth rectangle? So the area of the kth rectangle which will denote delta a sub k for area of the kth rectangle. Notice that that's just delta x of k, delta y sub k. Do you see why? So we would call this difference right here, we would call this delta x of k, and we would call this difference right here delta y sub k. And so what's the area of this rectangle? It's delta x of k times delta y sub k. And so then from the kth rectangle, we want to select any ordered pair from within it. What is the volume then of the kth column? Let's represent this two ways. Let's see what I was thinking there. Oh yeah. So the volume of the kth column would be our f sub x of k star, y sub k star, times our delta a sub k. What does a sub k stand for? The area of the kth what? Rectangle. That's that base. And what's this? What is this representing? The height of that column. Okay? But another way to represent that is as f sub x of k star, y sub k star, then times delta x of k, delta y sub k. And let's do it one more time, just because. That would be f of x of k star, y sub k star. And then what else could I do, folks? Well, these are both just numbers standing for the widths of the rectangle, so what could I do with their order of multiplication? Interchange them. So without going into Fubini's theorem, the fact that right here at this kind of molecular level of looking at this, I can interchange this multiplication has to do with why I'm allowed to flip the order of integration when we're integrating. Oops, delta y sub k, delta x sub k. Okay. So then what we're saying then is that the volume of the total region is approximately the sum from k, from k equals 1 to n of each of these, f sub x k star, y k star, delta a sub k. And we'll just write it just that one way. Okay. So folks, what we're doing here is we're going back. I mean, I kind of put the cart before the horse. I showed you the Riemann sum right here, and we're going back and we're building that. Okay. So the last thing we need to say is we will define delta to be what? The maximum length of all the diagonals in here. In this case, you have to go back and you have to look at what's our largest rectangle, and it's actually the one we've been working on. And in this case, this would be this length right here would be our delta. Okay. Then we're going to let that one way to look at it is we're going to let that delta start approaching 0. But if I start shrinking this down, and how do I want to say this? The way we'll do that is by taking another partition of this set. So we'll further subdivide everything. We'll have new rectangles. I'll have a new rectangle that's going to be the one with the largest diagonal, and I'll let that, then I'll think about making that smaller by giving a new partition. Okay. So as delta goes to 0, for this to happen, first of all, each delta a sub k will then be approaching 0, and n, which stands for the number of rectangles in the domain, is approaching infinity. Okay. And that's what I just said on this side. As the width of the maximum diagonal of all the diagonals go to 0, the areas of each of the rectangles go to 0, and the number of partitions becomes arbitrarily large. That's kind of as far as we're going to go into this. We'll save it for your future math classes for how you kind of spell that out a little bit better. Chance?
Is there a way to like find the length of the maximum diagonal without just moving through each one?
Right. So this is all being done theoretically,
Okay.
and we know that a maximum diagonal exists because there's a finite number of rectangles.
Okay.
But yeah, there isn't a way to actually observe that. So this would be something that, like a lot of our math procedures in practicality, this is a very tedious way to do it. And then what we do is we basically break things all the way down to our fundamental theorem of calculus part 1. Fundamental theorem of calculus part 2, and we have a faster way of computing these.
Okay.
Yeah. So no, I'm sure that there is a way to kind of, rather than if you're asking to check each and every one of them, there might be some sort of, first find the one of these that has maybe the maximum width. Find the columns that have kind of the largest widths. Find the rectangles that have kind of the largest lengths or heights, whatever you want to call it, and then go looking in that area. I'm not sure.
Okay.
So there may be a way to do it so you don't have to go through and check every single one. But it is meant to seem, not meant to, but it seems very, very tedious to actually do this process of refinements. And folks, we're not going to do it. If you remember back in Calc 1, what you did was you took an interval, you chopped it up into 2 pieces, and you approximated the area. Then you chopped it up into 4 pieces, and you approximated the area underneath the curve. And then maybe you did 16, and you approximated the area underneath the curve. But that's a very tedious way of trying to arrive at that limit through brute force. Okay, yeah. Okay, so here's where we fudged a bit. We've not discussed the idea of what it means to refine a partition. And the limit this limit that we're about to talk about is an exceptionally complicated limit. So here's our definition of the double integral. A function f defined in a rectangular region R, that's what we've been talking about, is said to be integrable if this limit exists. Okay. Now this limit has to exist for all partitions. What's a partition? It's the way you chose to chop up your domain? How many ways could you chop up the domain? Infinitely many. Uncountably many ways you could go through chopping up a domain. Okay? And it has to work for all choices of xk star, yk star. So what was that? That was your representative point from within each one of those regions. Okay? So the function has to be well behaved enough so that regardless of how you choose to create your partitions and then refine them, and regardless of which points you're choosing from within your partition, and then adjusting those points as you refine your partition, the limit has to exist, meaning it has to come out to the same thing every single time. Okay? So it's an exceptionally complicated limit, but if that's the case, then we go ahead and we say, then we'll call that limit the double integral over r of our f of x, y, dA, and that's that limit as delta approaches 0 of our sum from k equals 1 to n of our f's of xk star, yk star, delta, we'll just use the delta a, so k. Now folks, how do I remember this as I'm writing it out? Yeah, I'm simply remembering what it is we're computing. I'm summing up a bunch of columns. Each column has this height and this area of base. All right. So I want to show you, by way of a practical example, a way to interpret what it is we're doing here. Okay. All right. So here we have one way to talk about computing population is if you know the density of the area and you know the area, you can find the number of people, you can approximate that number of people in that region. Okay? So for example, for this town right here, here I've got this region right here which has a population of, or has a area of 1 square mile. Does everyone see that? The area of this rectangle right here is 1 square mile. What is the population density in that? Well, it's right there. Help me out, folks. What's the population density of that region? 450. So what is the population of that region? 450. How'd you get there? You took the number of people per square mile and you multiplied it by the number of square miles. Okay? So one way to interpret this, because a lot of times folks then become fixated on the idea of interpreting what we're doing as computing volume, which is always a mathematically sound way of thinking about this problem, but there's all sorts of real-world applications. If this shape right here represented population density, what would that mean? Well, wherever the z-coordinate is higher, that would correspond to having a higher density. You could imagine that as like the downtown of a city, right? And then this is, you know, kind of around this region here is the city limits, and then you get out to the rural area, right? So this is telling you the population density at any point in the geographic location. Then computing the double integral would be computing the population. Okay? So let's actually write this out here. We're not going to do the whole thing. We'll just set it up and then I'll give you the answer. So just as a reminder, what I've just said is that population is equal to the density times the area. And any time that you're taking a quantity and multiplying it to area, you can think about it as a double integral. So what we're saying here in our case is that the population is approximately the sum from k equals, let's actually literally do this, folks, from k equals 1 to what? How many columns will I be adding up here? 9, right? From k equals 1 to 9. And then we've got some density function where, how does that work? We take some x k star, y k star. So this is where this is just an approximation. It's not true that everywhere inside this red rectangle, the population density is exactly 450, right? Just like if there's 1, 2, 3, 4, 5, 6, I think I counted 14 of us in here. Okay? The population density of this room is 14 people per room. Okay? But in this room, there's pockets where it's more and less dense. Right? Over there, it's much less dense. Over here, it's more dense, etc. Does that make sense? So, but taking some representative point and giving the density of that point to stand in for the whole room, okay, that gives us a population density that we'll use as our height, and we'll multiply that by the area of the kth rectangle. So let's actually compute this, folks. This sum for the first rectangle here, it's going to have a density of 300, and then let's multiply it by the area of that rectangle. What's the area of that rectangle? Well, it's 3/2 times 1/2. For this first rectangle right here. Plus, for the second rectangle right here, that would be 350 people per square mile times 1 mile for its width times 1/2 mile for its height for that subdivided region. Okay. Then I'm just going to put plus ... and we end up with, for the last rectangle, we would have 200, I'm talking about this rectangle right here now, 200 times 1 times 1. Okay. And if you do this, let's actually compute this, folks. Help me out. 300 times 3/2 would be 450 times 1/2. I think I get 225 people for that first region, is our approximation for the number of people in that first region. Plus, then if we did 350 times 1/2, I get, what is that, 175? Times 1 for that next one. Plus ... plus the last region, which has 200 people in it. Okay. Then I went ahead and I summed this up before class, and I got 2,850? Yeah, 2,850 is our approximation of this population. Okay. Now, you could argue that, wait, how would you know the density without already knowing how many people are in there? I'll give that to you. This is kind of a cooked up example, but the idea is meant to show you how these sums are working here. Okay? And we're going to return and we're going to look at the iterated sums in just a moment here and see that, yeah, we're computing the same thing each time. Okay? Questions on that, folks? Oh, thank you, Andrew. So one of the things that, you know, if you read any calc book that they emphasize, it's that very quickly we jump into the iterated integrals in here. Like, if you think about like how much time you spent in Calc 1 on approximating Riemann sums, you did the right endpoint method, the left endpoint method, you did approximations, you did all sorts of work for quite a while before you brought in the fundamental theorem of calculus and you started rocking and rolling with your definite integrals, right? We're going to spend even less time on our original idea, okay? But because of that, students quickly forget what we mean by a double integral. And it's these sorts of examples that remind you exactly what a double integral is. Because the computation that we choose to do doesn't help us better understand what a double integral is. It's a shortcut for what we just showed here. All right. So we saw this in our pre-work where we wanted to develop an iterated type 1 integral. And let's go ahead and, I've got that it's 3:40, so let's take a quick pause. Alrighty, folks, so then we introduced the idea of these iterated integrals, which is actually going to be how we do our computation, like we did in the very first example of these double integrals. And so when we do a type 1 integral, the way we're going to look at it is we're going to integrate from some x equals a to x equals b. Where am I getting those from? That's my left and right hand limits of integration. And then what am I going to be evaluating in the integral? For each fixed x value, I'm going to be evaluating the area of that slice. And so in that sense, although I'll fill in what a sub x is in just a moment, an iterated integral is just an ordinary Calc 1 integral. So we think of the integrand as just some function of x. Okay? For each value of x, we're given a shape, and a sub x is the area of that shape for each value of x. Does everyone see how that picture works? Do spend some time thinking about it, because you can see that the picture isn't quite the same as we move throughout here. Okay? Now the question is, how do we represent that inner function that is the area of that one particular x slice? For this x value here, how do we represent this area? Well, this is again just an ordinary integral. For a fixed x value, we're going to have y values ranging from where to where. Does everyone see this? These are the y values. So the lowest y value will be right here. The upper y value will be right here. And when this is a type 1 region, we are able to describe it as having a function, a top function and a bottom function to this region. If we think of y as measuring heights, measuring top and bottom, I mean, like, usually think of this as kind of like elevation here, right, for the y. So I've got a lower and an upper versus a left and a right. So what could we do to represent that a sub x sitting inside of there? Well, that a sub x is going to be the area of this shape right here. And for a fixed x value, I'm just going to compute an integral in y. So this will be the integral from y equals, the lower value is going to be this green value right here. In fact, let me change the color of one of these. The lower value is going to be this green value right here, which I'm reading as, for the fixed x value, I can find its y coordinate through this function g of x. So that's y equals g of x. Let's do that in green. Up to y equals, and then the upper value, which I read, for this fixed x coordinate, it's this value right here. That's the upper y coordinate, and I get that from this function, h of y, or h of x, I mean. Okay. And then where do I get the height of this value from? I get it from the function f of xy. Now, in this formation of the iterated integral, for this function right here, at the instant that I'm integrating, and I need with respect to y, right? Integrating with respect to y. For this viewpoint, which of these two values is being held constant for that inner integral? X. So the way I want you to think about it is, we're on the outside, we're ranging, and this part's a little bit confusing, folks, and we'll get more practice with this, and actually, believe it or not, it gets easier as we get to triple integrals. Okay? But the way I evaluate iterated integrals is from what? I evaluate them from inside on out. Does that make sense when I say that? I'm going to evaluate these iterated integrals from inside on out. But the way I think about selecting each component is, first I work with the outside. I go to some x coordinate. Once I've chosen an x coordinate, then I go ahead and determine what this function a sub x is right there. So this, in this sense, for this inner integral, that's for a fixed x coordinate somewhere between a and b. Then I evaluate that. That's going to give me a specific output, and then I allow x to continue to vary. So it's a what we call a double integral, iterated. Okay? All right, so we'll get more practice with that when we get into our triple integrals. It'll be a little bit easier to think about it. But I just want to lay the foundation for this. We're letting x vary between a and b. Once we get a fixed x value, then for that x value, we allow y to vary, and we compute the area underneath that curve that's constructed there. That gives us a value, that gives us a number that corresponds to this area underneath the curve for that fixed x-coordinate. And then we move the x-coordinate on down. Okay? Now, it's not a discrete step because this is a continuous interval. So I don't like jump x by one more, but that's essentially what you can see almost depicted by this picture here. Okay? All right. So here's Fubini's theorem one more time. Fubini's theorem is what it's what makes evaluating double integrals straightforward. Up to your ability to set them up. Okay? So just restating it here. Recall that Fubini's theorem, which applies when f is what? Continuous on its domain. We can interchange the what of integration? We can interchange the order of integration. Going forward, you should be careful in the order that you pick. A lot of times it will not matter. Sometimes there'll be a slight difference in difficulty. Using one order might be slightly more difficult. But in some cases, I will give you integrals where if you try to integrate with respect to x, you won't have the tools, or you'd have to use some advanced tools like power series or some very advanced substitution techniques or something to be able to, or maybe you can't do it at all through elementary means. You couldn't evaluate the integral. But if you were to change the order of integration, then you could. Okay? So that is going to be one of the key topics to take from these, especially these first couple of sections, is how do I change the order of integration? Okay? So let's go ahead and re-explore that population density diagram in light of Fubini's theorem. So here we had this issue here. Here I treated this as what, folks? A double sum. By that, so this is the way we construct our double integral, right? The other way we could do this, though, is we could say the population is approximately the sum from n equals 1 to 3 of, and let me give some room here, times our delta x of n. So we're going to compute something inside here, and then we're going to multiply it by x of m. What would that stand for? That would be the width of the mth interval, right? How many m intervals do I have? Going from here to here to here, I've got a total of 3 of them, right? Oops, I think I said m. Those need to be consistent. That should be n. Okay? N and n. Okay? And then what I'm going to do inside of that is I'm going to compute the sum from m equals 1 to 3. This is the first interval, second interval, third interval, okay, of our d of x n star y m star delta y sub m. So how am I looking at this here, folks? I'm treating this not as a double integral, the way I did before. I'm going to, hopefully in a second, we'll verify that we get the same answer. But I want you to see what we're doing here. When n is 1, I'm going to say let's add up. We're going to be adding up things when n is 1. That has to do with the width of that first interval here. What am I going to be adding up? Well, inside of that, I'm going to go find this area right here. Okay? So if I go, well, let's just go ahead and write it out, and you'll see how this sum is working. Okay? So this would be equal to, what's my first width when n is 1? What's this first width here, folks? 3/2. So times 3/2. That's for when n equals 1. And we'll add to that plus something times 1 when n equals 2, plus something times 1 again when n equals 3, because these are all the widths of each of these when n equals 3, because the width of that is 1.5 or 3/2. That width is 1. That width is 1. And then what am I going to do inside of there? I'm going to do this sum inside each one of those. Okay. So inside the innermost one, we're going to add up what? We're going to add up the density times y sub m, which is a half for the first one. This was when m equals 1, plus the density, still in that first column, 450 times 1, that was when m was equal to 2, plus 400 times 1, and that was what we used when m was equal to 3. That was all for just the first column. So you see what I've done here, folks? I'm going to compute this area right here, 300, or think of it as like 300 times a half, 450 times 1, 400 times 1. Add those all up. That's doing that innermost sum, and then multiply that result by 3 halves, the width of that x column. So let's just start out this next one. What would this next one be? It would be, so this is in the second column, 350 times a half. Again, that's for m is equal to 1 again, plus 450 times 1 plus 100 times 1. Everyone see how that works? And when you add all these up, you do get the same thing. Sure enough, Fubini's theorem is true, and we sort of, in a way, know that for these discrete sums, it absolutely must be true, because we're just changing out multiplication and addition the way you know how to, the way you know how you can rearrange them by the commutative properties and the associative properties. So this one is like what type of integral? This whole thing is like what? What type of iterated integral? Well, so this one's more like the double integral. This one's more like the double integral, and this is going to be like one of our iterated integrals. What was the outermost integral, folks? It was like an integral taken with respect to x. So that is like the integral from x equals a to x equals b, and then we have the integral from y equals c to y equals d of f of xy dy dx, where inside for each fixed x value in this discrete sum, I did a y sum inside each one of them. So just for completion's sake, let's put what the population, we won't actually write anything out, we'll just say that the population is approximately, the other way we can do this is the sum from m equals 1 to 3 of our delta y sub m, sum from n equals 1 to 3 of our d of x of n star, let's make sure I'm using the same correct letters, am I consistent? Yes. Y sub m star delta x of m. Let's flip that over. Yeah.
Question, so the sum is 2,800.
Yes. Oh, it should be the same number. 2,850. Sorry about that.
Alright.
Shouldn't it be delta x sub n and then delta y sub n?
So here I've switched it, right? We did m goes with y, n goes with x. So m, yes, I see. I'm sorry. Anna, I should have doubted you. N goes with x and m goes with y. Great. And so what is this like, folks? This is like the iterated integral from y equals c to y equals d, integral from x equals a to x equals b of f of xy dx dy. It's like a type 2 integral. But again, no matter how you do this, you end up with the same 2850. Now, obviously this idea of interchanging or thinking about it as a summing up over rectangles or double sums over these intervals gives us the same value as long as everything's finite. The question is what about when things aren't finite, when we're taking limits of sums? And that's where Fubini's theorem actually comes into play. And it says we can do this, when can we use Fubini's theorem? As long as f is what? Continuous. Okay. So, you can actually work through these. I worked through them once about 3 years ago. Very, very tedious. You do some cases you have to do some trig substitutions, some W substitutions. It would be messy, but you can solve each of these integrals. Okay? I cheated this time around, and I just plugged them into a computer system. And you can verify this either directly or you can plug it into a system yourself. This comes out to be pi over 4. And when you evaluate this one, it comes out to be minus pi over 4. So what's the issue here, folks? Is Fubini's theorem broken? What's the issue then?
It's like the area above the curve and under the curve.
No?
Or I mean,
So Fubini's theorem up here says that evaluating a double integral is the same as evaluating either of these iterated integrals, and they will always agree with each other. But here I have these two iterated integrals, and notice it's for the same function. What's that?
It's not continuous.
The function is not continuous where? At the order pair 0, 0. Anna, I don't know if that was what you were going to say. You see that?
kind of.
Yeah. So at 0, 0, this function is not continuous. So no, it's not. Since f is not continuous at 0, 0, Fubini's does not apply. For those of you wanting this to be complete, there are functions that are also not continuous over the domain, but you still get the same answer regardless of the order in which you do the iterated integral. So just because Fubini's theorem doesn't apply doesn't mean the two iterated integrals won't agree with each other. They still could, but here's an example where Fubini's theorem doesn't apply and we got two different values for the two iterated integrals. And that should frustrate you. That should frustrate you. The issue here is, unlike this example here where I said it doesn't matter how you slice and dice it. When you add it up this way, you get 2850. When you add it up this way, you get 2850. When you add it up this way, you get 2850. It doesn't matter how you slice and dice it to add up and compute the population. In limit, if you don't have continuity, you're not guaranteed to be able to add up these infinite sums in any direction you want. Yeah?
So which way would you
Yeah, how would you, well, does it even make sense to talk about the double integral? Okay. And just like there are functions that are not differentiable, even though we spend a lot of time talking about derivatives, there are functions that are not integrable. But you know that if your function is continuous on the domain, then it is integrable, and you will be able to use Fubini's theorem. Yeah. Yeah. That's a good question, but it's yeah, that's good enough. Let's just spell it out here, folks, just to make sure. The picture that went with this, is we have some function that's living above our space here. What was our domain? Our domain was between 0 and 1. It was this rectangle right here. We can't compute the volume as f isn't continuous at 0, 0. How we doing, folks? So the issue was right here, my picture, oops, let's do a different color. Right here, my picture lies. The sketch that I drew above it were not actually continuous there.
So
So somewhere up here there's a problem. All right. This is actually just, this is a fun little application. It comes right from stuff that you did in Calc 1. How do you calculate the average value on a function? Okay. So if you want the average value of a function, it's equal to 1 over the area of R times the volume of that region. Does that make sense, folks? First of all, what do I mean by the average value of a function? Maybe if you were to take a snapshot in time right now and you were to look at the whole state of Colorado, okay, maybe I could come up with a function f of xy that says give me your longitude and your latitude and I'll tell you what the temperature is at that point in Colorado. Does that make sense? We took a snapshot in time, so it can't change with time. Okay? So we take a snapshot in time, we say, okay, we've got this function f, you input your longitude, you input your latitude, it tells you the temperature. Okay? Then, if the function, and so let me say that this is the average value of the function f. So what do I mean then by the average value of this function here? Forget about the computation for just a second. What do I mean if f is giving me my temperature at any point in Colorado? What would be the average value? What's that?
Average output.
Yeah, it's the average temperature across the state, right? Okay. Because, like, you know, and maybe maybe even just small locales, folks. Maybe you've experienced this if you're ever, you know, walking. Sometimes I walk. Where's that open space? Walk through that open space at night, and because of that creek there, you go down and it gets cool in certain little pockets, right? Okay. So you might have, you know, quite a discrepancy across small areas, but you still want to talk about what's the average temperature, and you'd be wrong if you used one of those. You know, if you use too close to a creek, maybe you're way underestimating the average temperature. If you're up on top of a hill, maybe you're way overestimating the average temperature. Okay? And so we compute the average temperature by summing up. So how do you compute an average usually, folks? Like if I say, give me your average for these 4 test grades, what do? You sum them up, and you divide by how much you had. So this is how we compute the average value of a function. So whatever this function outputs, its average output then is computed this way. Does that make sense?
Why is that how much we had the area?
What's that?
Why is that how much we had the area?
Yeah, that's a good question. It's that's a little bit hard to describe with my analogy there. Let's see here. The best example I can give just quickly off the top of my head would be actually from Calc 1. So maybe this is the temperature of just this spot in Colorado throughout the day.
Okay.
So here we have when the day starts, and here we have when the day ends. Okay. And so what we would do is, if this is the day starting, this is at time t equals 0. This is the day ending, this is time t equals 24, right?
Okay.
And so you would take and you would add up the temperature at all points in time across the day, but then divide by the total number of hours in the day,
And that would happen to be
and that would give you the average temperature. Yeah.
And we're just on one, so it's the volume.
So yeah, so in Calc 1, the average value we said was 1 over b minus a times the integral of f of x dx on the interval from a to b. That's how we did it in Calc 1. So I can't quite give you an analogy for...
But it makes sense why we're doing that now that you showed me what
Yeah.
we're doing there.
Cool. All right, so here we've got this question. Let's work it. Okay, let's actually work the problem. We want to find the average quantity, the average of the quantity 2 minus x minus y over this square right here. So, folks, I do think that it's nice to give yourself an inaccurate picture. And if you want, just always put not accurate. if it really bothers you to draw something that's not accurate. Okay. And what does our region look like? Okay. I did this on purpose just to practice this, right? What does x do? X varies between 0 and 2. What does y do? Y varies between 0 and 2. You see, I was able to write two statements at once with that one inequality. I'm not saying you've seen that before, but that's how we would say that. We okay with that? Nope. Yeah, so this is just a shorthand for me saying 0 less than or equal to x less than or equal to 2, and 0 less than or equal to y less than or equal to 2. Because these have the same left and right intervals, I could just write it that way with a comma between x and y. Yeah, Chance.
Don't we normally use the comma to like separate statements?
That's true. That's true. So this is a, just like a compound inequality. Really, like what does a less than or equal to x less than or equal to b mean? It means that a is less than or equal to x, and x is less than or equal to b. So it's just after a while we kind of just come up with more condensed notation. Yeah, to save us having to say multiple things. Yeah. All right. So we're asked for the average. One way to look at this is the I like to think about this as the average height of this function over the area. Okay. Another way of looking at it is like, remember when we had the population density example? It's like saying, what's the average population out of all of the Denver metro area if we take and if we compute the entire population over the whole region, and then we divide by the area of the whole region, that gives us the average population over the whole Denver metro area, not just the individual grids that we cut it up into. Okay. And this one has a very boring answer, but it's okay. So the average value is equal to 1 over the area of R times the double integral over R of 2 minus x minus y dA. Folks, for a while I encourage you to write out this double integral. Okay? Just to practice writing the double integral before you jump into an iterated integral. It keeps I promise you it's going to help you lay the right foundation going forward. Okay? So what's the area of A? First of all, let's answer that question real quick. It's 4. So this would be 1 over 4, and then let's pick a specific iterated integral. In this case, I don't think, so notice here that my region is what? Square rectangular. I don't think that one particular method is going to be favorable to the other, so I'm just going to say let's go x equals 0 to x equals 2, y equals 0 to y equals 2 of 2 minus x minus y dy dx. So this gives us 1/4 integral from 0 to 2. This would be 2y minus xy minus 1/2 y squared, evaluated between 0 and 2, dx. So let's see here, that'd be 4, well, I guess 4, and that's 4 minus 4. 2 is 4. I think we get 2 minus 2x. Double check me, folks. How we doing, folks? Okay. Shout out a question if you got one. It's a great time for it. And so we end up with 1/4 times 2x minus x squared, value between 0 and 2, and oh, it comes out to be 0. Pretty boring. Yeah, shucks. Let's look at a picture of that. Okay? Because remember I drew that picture a moment ago and I said it wasn't actually the accurate drawing? Let's look at it slightly, it's still not going to be accurate, but let's look at it slightly more accurately. Here was our region here. And our function is what type of function, folks? What type of object is that function? What is it?
A line.
Not a line. It's a plane, right? And so one way to look at it is this is the plane Z is equal to 2 minus x minus y. And so we could actually draw the, we could actually sketch this plane, because when, if we want to find the, for example, if we want to find the z-intercept, the z-intercept is 2. Oops. And if we want to find the x-intercept, that is also 2, and the y-intercept is 2. So these have intercepts 2, 2, and 2. So this is actually, even though it's got a boring answer, this is the reason for it. Here's our plane, and you can imagine this. Let me draw it like this, I guess. Here's our plane, and so this plane dips below our region right there, and it precisely balances out. Like if you were to look at projecting this down right here, that's what we have if you were to actually look at the graph of this. Half the plane lies above the surface, exactly half the plane lies below the domain. And so what's the average height of this plane? The average height of this plane is 0. So even though it has a boring answer, I think I took this example from the book. The reason why we picked one with a boring answer is because it was easy to graph and actually see why the answer is 0. Questions on that, folks? Okay. I want to do a real quick discussion that we don't have time, that we're not going to go into detail for. If you go on to take further calculus courses that are basically like repeating, just going through everything more carefully, you would actually derive why this works. When we developed our double integral, we did it assuming we had a what region? Rectangular region, but we've already looked at our 16.2 pre-work. We've learned how to do these double integrals for non-rectangular regions as type 1 or type 2 integrals, right? And so the issue here, what we're going to do is notice that if we were to come up with this partition of our region R here, notice that some of our rectangles lie completely in the region. Some of these rectangles lie completely outside of the region. And then some of these rectangles lie on the boundary. Do you see that? So if I were to color code those rectangles as red if they lie entirely inside the region, as purple if they lie on the boundary of the region, and as blue if they lie outside of the region, what I could do is notice that as I further subdivide this, the amount of area that's purple becomes less and less. And I would get a better and better approximation for the true area. Okay? And then what we can do is we basically define this new function, f of xy, and it would be equal to little f of xy if the xy is contained in the region, not the real numbers, sorry, in the region R. And it's equal to 0 if f of xy is not contained in that region. And in limit, taking the double integral over this will give us the double integral that we're after. So all that, and if I lost you on that, that's okay. What I'm saying here is that all of this can be redeveloped for non-rectangular regions. You just define a piecewise function on your non-rectangular region that agrees with your function if you're in the region and is 0 if you're outside of it. Because what's the volume if my underlying function is 0? It contributes 0 volume to it. So all of this can work out for non-rectangular regions. And now we're ready to do a hard problem. So I'd like you all to try this. Okay? And this is a tough one, but this is what we're gearing up for, being able to do these problems. Give it a shot. Yes? All right, I'm going to go ahead and jump in now. I'm not sure, I think many of you are working through this. You may be on the right track. It's a little hard to tell, just quick over the shoulder. But as I look over the shoulders, I saw very few pictures drawn. I think it's very hard to do this problem without actually sketching your region. Okay? I think you'll be a little bit surprised by this when we take a look at it. So let's go ahead and give it a shot here. If we were to sketch our region, which is the first thing you should do, let me first draw the graph of y equals x, or excuse me, x equals y cubed. So this graph looks like this. And then let's draw a graph of y is equal to x. Yes. And then if we were to, it turns out, and we'll be careful about this as I draw it, but let me just put this all up here. Here's where y is equal to 1, and here is where y is equal to 2. So first of all, where do these two coordinate lines intersect the first time? Where do these two lines intersect here? What's that intersection?
1, 1.
Those are the coordinates 1, 1. Are we okay with that, folks? How do we get that? Well, it's where y is equal to y cubed. And although there are a few solutions to that, the one we see in the first quadrant is when y is 1. And when y is 1, since x is equal to y, we're at the point 1, 1. We okay with that? No? Yay? I need some feedback, folks. We good? Or we? Because I can talk about it. All right. So if we were to go ahead and solve this, we'd get 0 is equal to y cubed minus y. So we get that 0 is equal to y times y squared minus 1. Or 0 is equal to y times y plus 1 times y minus 1. So we get 3 y coordinates where these two curves have the same y value. That's y equals -1, y equals 0, y equals 1. Then I just plug y equals 1 into either of those two functions to get the x coordinate. So that's where we get the order pair x 1, 1. And then our y coordinates have to go between 1 and 2. So there's this line right here, and then there's this line right here. So I'm also going to need to find this point right here. Oh, so what's my region here, folks? I picked this one on purpose because it's a difficult region. What's my region here? I got to pick y values between here and here, and my x has to be between these two curves. So x has to be between this curve and this curve as we're in this interval. So what's my region? If I were to shade that, running out of color choices, if we were to shade that, it would be this it'd be this region right here. Everyone see that region? Okay. I picked that one on purpose. It's a messy one. Okay. Most people, even if I asked you to draw it, which that should be your first thing to do when you do one of these regions, a lot of people get the wrong region even when they sketch it. So what are we going to need to find? Well, let's go ahead and find this coordinate right here. Well, we know the y coordinate is 2. And since we're on the line y equals x, then the x coordinate also has to be 2. So that's the order pair 2, 2. And then I also need this intersection point right here. So that's where the green x cubed curve hit the line y equals 2. So that happens when x is equal to what number? Oops, I just wrote it down. That happens when x is equal to what number? 8. We okay with that? So I'm looking for the point that's on the line y equals 2. So we know the y coordinate had to be 2. And on this curve, green curve right here, which is the curve x equals whatever the y coordinate is cubed. So that's how we got 8, 2. We okay with that? All right. So now we can go ahead and set up our double integral. So our double integral that we're trying to evaluate is the double integral over our region R, there's R, of e to the x over y dA. Now that I've drawn the region, which I think is actually one of the hardest steps for these problems, and everybody, when you work these problems, you should draw a region. Go ahead and set up your double integral now. Pick an order of integration. So you're setting up an iterated integral, right? So you're either going to integrate with respect to x on the outside or with respect to y on the outside. If you're not sure which one's easier, set them both up and then look and decide which one you want to do. So one way you could integrate this, please don't erase your work if this is not what you put, but jot this down. This is one way you could integrate this. Notice I'm integrating this as a type 1 region. Everyone see that? Now, because if I'm doing it as a type 1, what I have to do is I have to split it right there because the upper and lower functions change as I'm going from left to right. Does everyone see that? So from x equals 1 to x equals 2, it was the cube root of x curve on the bottom and the x curve on top. And then from x is equal to 2 out to x is equal to 8. There's where x is 2, there's where x is 8. It was the purple curve, y equals 2 on top, and the green cube root of x curve on the bottom. Does everyone see how we can set that up? Now, in previous classes, you might have said, oh, that's 2 integrals. I don't want to integrate it because it's 2. Maybe I'll try the other way. I'm here to tell you that's not necessarily the thing you should be most scared of. Look at trying to integrate e to the x over y with respect to y. Right? You treat x as a constant. I can't integrate that through elementary means. You could come up with the Taylor polynomial for that, the Taylor series for that, integrate it with Taylor series. You could try some other method, but I think that that's way too hard to integrate. So instead, that was as a type 1. I think we should set this up as a type 2. So here we go, setting up as a type 2. We're going to go from y is equal to 1 to y is equal to 2. X is equal to, so let's see, the leftmost curve is y, and the rightmost curve is the green y cubed curve, x equals y cubed, of our e to the x over y dx dy. So the wrong takeaway message was to take from this is, oh, one way had 2 integrals, I'll try the other way, because that's not necessarily going to be the case. Sometimes evaluating 2 easy integrals is better than evaluating 1 impossibly difficult integral. Okay. So this is integrating the function e, basically integrating e to the x with the constant 1 over y in front of it, right? So that's a real baby u substitution there. So this would be the integral from 1 to 2 of 1 over, y e to the 1 over y from x equals y to x equals y cubed dx. If you don't believe me, I'm sorry, I have a mistake there. Christy says that doesn't look right. That should be x. Thank you. Okay. And if you're not sure, how do you always check, folks? If you just integrated, you want to make sure you did it right, what do? Take the derivative with respect to x, and sure enough, we get back to where we started. Okay. So, evaluating this, we've got the integral from 1 to 2 of y e to the y squared minus y e to the first, which is kind of alarming to see, just a e sitting there. Does everyone see why that's e? We okay with that?
Yes.
No, it should be dy.
Yeah.
That should be dy. Yep. How we doing, folks? Okay. Now notice this integral here, the integral of y e to the y squared. Now it's still a u substitution level integral, but it's not an impossibly hard one like the first one was. Okay. So we can go ahead and integrate that, and let's see here, we end up with 1/2 e to the y squared, double check, yes, e to the y squared times 2y, yep, minus 1/2 y squared e, evaluated from 1 to 2. And I'm just going to go ahead and go to the answer here because we're running out of time. And so if you evaluate this, you end up with 1/2 e to the 4th minus 2e minus a term 1/2 e minus 1/2 e. It goes to 0. Get that one out of the way. And so we just end up with an answer of 1/2 e to the 4th minus 2e. I guess all I did was write out what you would have gotten. Thought I'd save some time. Folks, you see what we did here? I want to make sure we do. Okay? It's very easy to kind of get complacent as soon as you get into the iterated integral to forget what it is you're computing. So just as a reminder, here's x, here's y. This would be our region right here. In the xy plane. And then we've got some function who lives above it. And what we're doing is what we're doing here is computing the volume. And by volume, I always mean net volume in here, folks. The net volume of that region. That's solid. So the moral of this story, and you saw this in your pre-work, was making a decision whether to integrate something as type 1 or type 2. How are you going to know which way to do it? You're not going to learn from any one problem. What do you have to do? You got to work lots of problems, and then you'll start to develop an intuition. And it could be, like in the real world, it could be that neither way works out. You know, nothing says that any function has, I mean, even though it's integrable, that you can easily come up with its antiderivative, right? In the real world, all bets are off. But for the problems I give you, how do you know which way to integrate? Oftentimes one way will be far better than the other, but you won't know until you've practiced a lot of problems. All right. When we come back, we'll do a little bit more I want to draw one quick picture right here for number 28. How do we find the volume of a region bounded between two surfaces? Well, what we're asking for is, let's say we have this region here, R, and then we've got this surface, f of x, y, and that would be, we could be talking about this here, and then we've got another surface, some g of x, y, and we've got this region here, and we want to talk about computing this volume between these two surfaces. Now, well, in practicality, these will be hard problems to do. I think conceptually we should be able to say, what will this answer be? How would we find this, folks? What will we do to evaluate this double integral?
And the volume beneath g of x and a minus of that volume beneath f of x, y, both f of x, y.
Exactly. And we can actually do that just like we did in Calc 1 in one fell swoop. So the way we can do that is the volume would just be the double integral over r of our upper minus our lower, creating a new function that does that difference. So Gabe is exactly right. What you could have done is you could have found the volume between the xy plane and g of x, then the volume between the xy plane and f of x, and subtracted the upper from the, subtracted the lower from the upper. But you can build a function that does that difference right off the bat, and then evaluate that, just like we did in Calc 1. So what we'll come back to, folks, is I'll work this problem next time. I'll start on this problem next time, number 29 here, where we're going to find the volume of this region here. Okay. But hopefully you see that the hard part will actually be coming up with describing this region. The easy part will say, oh, the upper curve is that plane, the lower curve is this parabolic cylinder, and so the integrand will just be the upper minus the lower. Now, you might be asking, how would I draw this? Okay. One, I would say keep practicing these problems, because you will get better as you go along. I'm not going to give you an impossibly difficult problem to draw, but you want to keep practicing these. I think if you're looking for the right level of difficulty, look at the practice exams, where I've got a whole bunch of these where the sketches help you out. Okay? I think that if it's something where about this complex, because of that slanted plane there, I would probably share this image with you. But if the situation were less complex, like a paraboloid that opens downwards and a paraboloid that opens upwards, I think it would be fair game for me to expect you to sketch that. Okay, to recognize, oh, this is a paraboloid opening downwards, this is a paraboloid opening upwards. That would be fair game for me to expect you to sketch and then be able to come up with the volume on your own. Okay, folks, next time we're going to get more practice. You're going to be doing double integration, but you're going to be doing it in the polar coordinate system that you learned in Calc 2. Okay? Your pre-work first reviews the polar coordinate system. Okay, I know it's possibly you've forgotten it. No worries. It first reviews that, and then we get into some polar integrals. So grab one of these on your way out. Then we jump into triple integrals. Triple integrals have a domain that is in R3, not on the x-axis like it was in Calc 1, not in the xy plane like it was now, but we take some domain value from R3. I'll let you take a look at that. So grab one of these on your way out, or I can pass them out to you, whatever's easiest. Just have to come grab them. There are the announcements one more time. Oops, there they are. Let me know if you have any questions, folks. I do have office hours staying around here until 5:30, so if you want to stick around and ask some questions, I think that's a great thing to do. Have a good day, folks.